This is a very brief overview of graphs of functions. We're reviewing some of the concepts that we learned in college algebra. So first of all, looking at continuity, a function is continuous if you can draw it without lifting your pen from the paper. So looking at this, where can I see that it is continuous? It would be continuous since this has an arrow, it keeps going out to negative infinity. So from negative infinity on the x-axis all the way to 2, we are continuous. So we would be continuous from negative infinity to 2, and then again from 2 to positive infinity, because again it keeps going out this way. So we would go union 2 to positive infinity. That's where we're continuous. Only at x equals 2 do we have a point of discontinuity. Here's another type of discontinuity, a vertical asymptote. This has a vertical asymptote at x equals 2. And again, from negative infinity out here on the x-axis all the way up to 2, I can draw this piece of the graph without lifting my pen from the paper. So we're continuous again from negative infinity to 2, and then again from 2 to infinity, just like this other graph. So here, I am able to draw this graph completely without lifting my pen from the paper. So this would be continuous from negative infinity to positive infinity over its entire domain, all real numbers. A graph is increasing where it goes up as we read from left to right, and a graph is decreasing where we go down as we read from left to right. So here, my graph is increasing because as I read from left to right, the graph is going up. Here it's going down as I read from left to right. And so this one is decreasing. And then this one is neither going up nor going down as we read from left to right. Such a graph is constant on that interval. So here I am decreasing on this branch. So where is that? That's from negative infinity out here on the x-axis all the way to 1. So I'm decreasing from negative infinity to 1. And then it is increasing between 1 and 3 because the graph is going up on this interval. And then it's constant on this interval. So it's constant from 3 to infinity. Okay, so here again, it's a constant function when it's not increasing or decreasing. And so a line, like y equals a number, is constant on its entire domain. Now, a function has symmetry across the y-axis if I can replace x with negative x and end up with the same thing. This type of function is called an even function, and a good example of this is y equals x squared. We look at y equals x squared, it looks like that, and it's symmetric across this y-axis right here. If I can replace x with negative x and I get back the opposite of what I started with, this is an example of an odd function. An odd function is symmetric about the origin, and x cubed is a good example of an odd function. If we look at this, we see the same piece over here rotated this way. That's what we mean by symmetric about the origin. If I cut along the y-axis and rotated this half of the graph, it would lie on top of this half of the graph. So this is a summary. An even function has this property, and an odd function has this property. Absolute value can be written as a piecewise function. Oh my goodness, they made a mistake on this slide. That should be a negative x. So it should be just leave whatever's inside alone if it's already positive, and make it negative if it's negative, because a negative times a negative will be positive. What that means is over here where the graph is already positive, the positive values of x, it's just y equals x is a straight line that goes through with a slope of 1. Y equals negative x is what we'll have over here on the negative values of x, and that's a graph that looks like this, and that results in that absolute value function, which has this sort of graph. So here's a picture of that. We see the negative x on the negative x values and the positive x on the positive x values. Our Our domain is all real numbers, and our range is 0 to infinity, including the 0. So we're symmetric with respect to the x-axis. If I can replace y with the negative y, and it ends up with the exact same equation. An example of this would be something like x equals y squared. X equals y squared, as we're going to learn coming up in this course, if we don't already remember from college algebra, is a parabola that's on its side, like so. This is symmetric across the x-axis. This half looks like this half. If I add a number to the outside of the function, it shifts me up or down. Up if it's positive, down if it's negative. For example, we know that this looks like the graph of y equals absolute value of x. Because of that, we just went over what that graph looks like. This is shifted down 2 units. So I would subtract 2 on the outside of the function. This is shifted up 1 unit. So I would add 1 on the outside of the function. If I add or subtract inside where the x is in the expression, then that shifts me left or right. It shifts me to the right if I subtract, and to the left if I add inside. So for example, again, this is our absolute value shape, but it's shifted. So I know I'm looking at absolute value of x, but here I'm shifted right 4. So I'm going to replace this x with x minus 4. Here I'm shifted left 2, so I'm going to replace this x with x plus 2. All right, so if I have both a vertical and horizontal shift, I can see that here. Here I'm shifting the absolute value of x, left 2, down 6. So I would go left 2, down 6. Now let's go back to the previous, I can't really. Excuse me. So since this is a minus 2, this is a right shift of 2, up 8. So I would go right 2, up 8. Okay, so now here, this is the graph of my basic function here is something squared. So this is the graph of y equals x squared, a parabola, but it's been shifted right 1 and up 2. Right 1, up 2. Now, the domain of a parabola is all real numbers, so it doesn't change the domain. But for a parabola, we normally have a range of 0 to infinity, but it's been shifted up 2, so that's going to change this range to 2 to infinity. Now here, the basic graph is y equals x cubed, because I'm looking at something cubed. I've been shifted left 1, down 2 because of these transformations. Notice that the original domain and range of x cubed is all real numbers. So shifting left 1 and down 2 doesn't change that at all. Now this is the basic graph of y equals the square root of x. And the domain on this basic graph is 0 to infinity. And the range is 0 to infinity. But I've shifted it right 2, down 3. Right 2, down 3. Inside, outside. So the domain is shifted right 2, so it's going to be 2 to infinity, and down 3, so the range is going to be negative 3 to infinity, like so. Okay, so here we're talking about that. We just went through that. We went up 2 for the range. So this is still all real numbers for both of them. You can pause on these slides to read them or look at the slide handout I gave you. And here we just went through the new domain is 2 to infinity, the range is negative 3 to infinity. If I multiply outside the function, that results in a vertical stretch or compression. Stretch if it's bigger than 1, compression if it's less than 1. So for example, absolute value of x is my function here in blue. 2 times, 3 times, or 4 times stretches the graph vertically. But a half times, a third, 0.3 times, and 0.1 times compresses a graph vertically. So it makes it go down more when I'm compressing. If I multiply where the x is inside the function, that's a horizontal stretch or compression. It's going to be a stretch if I'm less than 1 and a compression if I'm bigger than 1. These are sometimes hard to see on a lot of our algebraic functions. If you've already taken trig or if you take trig next semester, it's easier to see the horizontal stretches and compressions with those trigonometric functions. But here, a half times the x stretches me horizontally, and 2 times shrinks me horizontally as compared to the original graph. Now, if I put a negative on the outside, that reflects me over the x-axis. A negative on the inside reflects me over the y-axis. So here we can see that reflection across the x-axis with the negative on the outside, and a reflection across the y-axis with the negative inside where the x is. Okay, so if I look at the graph of an absolute value of a function, that takes everything and makes it positive. So it flips the bottom half of the graph up. So if this is my original function, then sticking an absolute value on it makes that centerpiece that was negative now just reflect up into the positive axis. So the easiest way to graph this is to graph the original function with the shift and then just flip it up across the x-axis. Now, with an absolute value, remember your range is just positive values, 0 to infinity. So it's going to flip the range up to 0 to infinity instead of being down here at -3 to infinity like it is on the original function. Now, to solve an absolute value equation, if I have something, the absolute value of something equals a number, well, absolute value takes something and makes it positive. So the original expression could have been the positive or it could have been the negative. So I formed 2 equations, set that what's inside the absolute value equal to the positive and to the negative, and then just solve it like normal. Subtract 1 from both sides, divide by 2. We get 2 answers. Plug these back in for x in the original expression to check and make sure that they work. That's how I'm going to solve an equal sign. If I've got an equal, an absolute value equals something, set it to the 2 equations like in the last example. If it's an inequality, look at the way the inequality is. If it's bigger than the number, I'm going to set the expression inside the absolute value bigger than the positive or less than the negative. If it's less than the number, then I'm going to set it in between the negative and the positive. And let's visualize why this is really quickly. If I'm looking at an absolute value equals k, well, that means it could have been a negative k or a positive k, because the equal to is the same distance from the origin 0 in the negative and positive direction. So if I'm bigger than k, then I'm bigger than the positive out here or less than the negative out here. If I'm less than k, that's inside here where it would be, the absolute value would be less than those 2 extremes. Okay, so if I have 2x plus 1 is bigger than 7, I'm going to set 2x plus 1 bigger than 7 or less than -7. Then just solve each equation as normal. Subtract 1, divide by 2. We get x is bigger than 3. That's this interval. Let me move this out of the way a little bit so we can see. Maybe I can't. Okay, bigger than 3 is this interval. Less than -4 is this interval over here. And then I have 2x plus 1 less than, in absolute value, 2x plus 1 less than 7. Well, that's the inside, so I'm going to go between -7 and 7. So set up the 3-part inequality like this, then go ahead and subtract 1 from each side. We get -8, +6, divide by 2. Our solution is in between -4 and +3. Now, notice that I can also look at the solution graphically. The equal to, if I graph the line, y equals absolute value of 4x, 4 minus 3x, this one, and the line y equals 2, the red line here, the solution to A is where the two are equal. So that's here at this point, which is 2/3, and this point, which is at x equals 2. Where it's bigger, the absolute value is bigger, would be here and here. The blue line lies above the red line. So that goes from here this way. So negative infinity up until the 2/3. And again, from this way, so 2 to positive infinity. And then where I'm less than is in between. The blue is less than the red in between the two. So our solution here is 2/3, and that should be a bracket, 2, 2, bracket, and it's a bracket because it's an equal to included. If it were just a greater than, then we would use parentheses. So C has this as its solution. B has the opposite, negative infinity to 2/3, union 2 to infinity. And again, I need brackets here because of the equal part of the inequality. And then the equals is two values, x equals 2/3 and x equals 2. All right, guys, that gives you enough information to complete this homework section. Please watch the videos on my math lab and work that homework set and let me know if you have any questions.